All right, so let's get started. Welcome everyone to Erica's thesis defense. As is tradition, the advisor has to make some beginning, sometimes embarrassing remarks about the student. And a lot of you have shared pictures. I think Casey Brinkman had the record of, I think it was 20 minutes of introductions. It was a very nice long introduction. I said to Erica, I'm going to be short, but I've got quite a few slides, so we'll see. All right, so who is Erica Bufanda? Family members have kindly provided some photos of her as a young kid. We can see in the right-hand picture, she's looking a little bit grumpy there. I've heard that she can be strong-willed, and Erica shared with me this morning that the family called her Mega Mouth. And this was in the context of us wondering if she could protect her voice and everyone could hear. But apparently this just means she was determined to go into astronomy and go far with her career. And so even at a young age, she was interested in astronomy and Star Trek, persevered getting her degrees. After graduating from high school, she went to college and then made her way to Hawaii. I know that family is extremely important for her. She's got three family members here today. Now, I first started interacting with Erica in 2017, where she became the TA for my undergraduate astrobiology class. And up until this point, she had been focused in other areas of astrophysics, but found she really, really liked astrobiology. This was spring of 2017. At this point, she decided for personal reasons to take a year of leave to support her family. And right at the end of that spring, she decided she wasn't happy with her first research project. She would rather switch to astrobiology. And the graduate oversight committee said, no, you're too far into it. Finish the first one. You can do the second one with Karen. So she took her year of leave off. In the spring of 2018, she contacted me and said, I really want to switch my project. And so the committee said, okay, but she had to do it in a very short time period over the summer. It was due in September. And she had a full-time job. She was teaching summer school and at the Griffith Observatory. Nevertheless, she managed to get the best 699 project of that cohort, and in fact did the same thing for her second one. Now, Erica's really into outreach activities and mentoring. We've got Girl Scouts, we've got a YouTube video at the top. She's taught the Observing Lab course a number of times. And remarkably, she forged a collaboration with an avid amateur astronomer at the DeKalb Observatory and had to do a really sudden turn during the spring when she was working with him when he suddenly passed away and had to totally revise the course. She also mentored 3 REU students with the Comet group during the pandemic, so everything was over Zoom, so she was really invaluable there. She's been at a lot of meetings, and what really impressed me was her very first big science meeting, the Division for Planetary Sciences meeting in 2019. Unlike most students who elect for a poster talk, she did a big oral talk, and it was very well received. So I've taken her to a lot of places where she's had really great networking opportunities at the meetings. Now, one really nice opportunity she had was I invited her along with some others who invited her to participate in 2 think tanks with the Keck's Institute for Space Studies. And you can see she really has fallen in love with the solar system. Does anybody see the strange solar system object in the second think tank photo? Yeah, this was a really exciting event. It was a small group, about 24 people, where you're really working on trying to solve innovative problems. And this was on exploring rapid objects, difficult things, long period comets, interstellar objects. And we got to tour some of the facilities at Caltech to see some of the instrumentation they're developing. And one of the reports just came out this summer, so a big document. Now, she's won quite a few awards, one of which was the Seroptimus Award, because again, it was still in an era where people are a little bit worried about the pandemic. The award ceremony was actually over Zoom, 150 people in the call. And I took good notes during the ceremony. So I do have the words that she said. She started out with, I'm a first generation college student, the first to obtain her degree of a wide diversity of heritage, Chinese, Thai, Hungarian, and Russian. One of her highlights was to attend a Star Trek convention dressing up as a Ferengi. And the family did not send me a picture, so I had to look up a female Ferengi. I hope that's close enough to what you look like. She's also been given recognition for her presentation at the SACNES research talks, which was really prestigious. In 2019, she took my grant writing class, and so this is a pitch for grant writing. It did, in fact, help her get one of the prestigious finest fellowships for her graduate support. Now, our group usually met every week as a COMET group, and during the pandemic, it was often over Zoom. And one year, she doctored up one of our Zoom meetings as the group Christmas card, which I thought was kind of fun. Now, she's had a lot of other activities while she's been in grad school. Some of these are all things that other students have sent me without any discussion of what they were, but it just looks like I have no idea what the cat in space is about or the alien glasses on Erica, but she's really engaged with all the community here with activities outside of just doing science. And I know she's extremely dedicated to the paddling in competitive races, and I think your team has won some of these races. So where to next? Her next step is she's got a postdoc at the University of Edinburgh with Cyril Opitom. This starts on September 1st. Now, she's been ramping up to try and get ready to go to Edinburgh. And so I wanted to do just one last experiment because I've been working on some big workshops and delving more and more into AI. So I fed this picture to AI, and here was the prompt. I'd like a caricature of Erica finishing her thesis. That's what came up. And I thought, this doesn't look quite like Erica. Let's see if we can refine it. Make her hair longer, her face a little bit rounder. But no, this is way too happy. That's not what you look like when you are trying to finish your thesis. I said, make the desk messier, more stressed, and put photos of comets and telescopes in the background. This is Erica finishing up her thesis, and I thought, no, let's add a little more stress. So I said, please add some coffee. So here we are. We're trying to finish up the thesis and get ready for the defense. So in the spirit of AI, to transition to her talk and giving you the title of her talk, I fed her title into ChatGPT, and I said, please make a graphic based on this title. So her thesis defense will be Vehicles to the Past, Characterizing the Activity of Long-Period Comets. This is what it came up with, and it explained this shows comets, solar system science, missions, and doing scientific work on comets. I thought, okay, I like it. All right, so with no further delay, it only took like 12 minutes. Let's welcome Erica. Well, they're hunting that up. Nominally, we have about 45 minutes for the talk, questions from the audience, and then just the committee voting.
All right. Thank you so much for that really nice and thorough and interesting introduction, Karen. Wow, what a blessing and honor it is to be surrounded by so many colleagues and loved ones, and to finally have reached this day, 7 years in the making. I'm just extremely grateful. So I just want to highlight some sources of funding before I continue. Karen has touched upon this already, but the NASA Finest Grant, which helped fund my last year's study, the Seroptimus Founder Region Award, which is gifted to women in assisting in helping them complete their PhDs, the Hannah Liebrig Teaching Award, which I received for my time as an instructor, as a TA that helped fund over half of my time here, as well as the George and Mona Elmore Achievement Award for College Scientists. So thank you very much to everyone associated with those sources of funding. So I know we have a lot of people from various backgrounds here. So I'm going ahead and start off with a very broad introduction. Sorry for all the the experts in the room. So we're going to start off by figuring out and covering different definitions associated with comets. And so what are comets themselves? Many of you have seen them as these spectacular objects in the sky, often characterized by the existence of a gas and or dust tail. Now, this arises from outgassing on the surface, a process called sublimation, which is the ice to gas transition on the surface of the comet as it gets closer to the sun. It lifts off observable dust grains in the process, and that's what creates this large sweeping dust tail. Now, comets usually have some of the most eccentric, which is another word for elongated, stretched out, elliptical orbits. And so we like to refer to them in terms of their orbital properties. So perihelion refers to closest approach to the sun. Aphelion is the furthest approach in their orbit. And so those will be terms that I'm throwing around a lot in this talk. So comets are found in many different places in the solar system. I'll be focusing on long period comets. But if we start for a sense of scale here on Earth, we are 93 million miles away from the sun. So that's 1 astronomical unit, 1 AU. If we go out to Jupiter, that's 5 astronomical units, roughly 500 million miles, already quite a road trip. And then if we go an order of magnitude further to about 50 AU, we have the Kuiper Belt, which is where our beloved Pluto lies. A lot of people like to think that it was demoted to a dwarf planet or a Kuiper Belt object. I like to think it was promoted because my unbiased opinion is that small bodies are a lot more interesting than planets. So 50 AU, that's where we're at, 5,000 million miles away. That dusty donut, that's the Kuiper Belt. And then if we go even further to the outskirts of our solar system, thousands to hundreds of thousands of AU away from us, we are surrounded by a debris field, a spherical debris field of material that was left behind by the tumultuous time, which was our solar system's birth. This is known as Oort's cloud. And this is where long period comets come. So what happens is material in this icy debris field gets gravitationally disturbed by a passing star or any kind of gravitational force that has the ability to alter its orbit and gets sent inwards to the inner solar system, where we observe it for the first time as a long period comet. Now, we study these small bodies because they are some of the most primitive bodies in the solar system. You can imagine that in the early protoplanetary disk, that's the disk that was before the formation of our solar system, kind of a conglomerate of ice, gas, and dust. And it was a mosh pit of sorts. A lot of material being swung or being gravitationally thrown in every direction. Some of it coalesced to form the planets. And some of it got swung outward to outskirts where it gravitationally settled in the Oort cloud, and it stayed there for billions of years in cold storage. That material eventually became a long period comet, and so you can imagine that the chemistry of the protoplanetary disk is preserved. And that's why it's interesting to study these small bodies and why I like to refer to them as vehicles to the past, because they allow us to look back in time to the early formative processes of our solar system. I'll be talking about 2 different types of LPCs today. The first is dynamically new. That's that situation that I described, fresh from the Oort cloud, some of the most primitive, unaltered material. And then the theory goes that once we have these dynamically new comets coming in, they get close to other planets or other things that gravitationally disturb their orbits, and that alters their orbit again. And for a lot of these, the orbits get less and less eccentric and more confined to the inner solar system. After several orbital iterations, this effect becomes more prominent, and we like to refer to these comets as dynamically old. They've been around the block a few times, so to say. And so this is how we refer to their dynamical age. The natural question is, what's the relationship between these 2 populations? Jan Oort himself in the 1950s gathered a distribution of dynamically new and old comets and compared them to what we would expect from theory.
And so if we look at this plot, the number of comets is a function of comet energy. All you really need to know is dynamically new comets are here, dynamically old comets are here. And this is what theoretical observations predict the curve should look like. So there's a discrepancy between theory and observations that suggest that we are missing dynamically old long period comets. Where do they go? And so the natural process of things is developing theories for explaining why they're missing. Jan Oort himself postulated that this could be due to the processing of the surface of the comet being out in the outer solar system for so long. High energy materials interact with the surface, creating a volatile frosting so that when the comet comes in, it's wildly active, and then that activity is spent and it fades thereafter. Another explanation is thermal fracture. Dynamically new comets break apart. And there's a lot of conjecture that's still involved with the thermal processes behind, or the physical explanation for why these comets are missing. So I'd like to take an aside to actually talk about the thermal evolution of the nucleus. It's intimately tied, it's believed to be intimately tied to the observed activity of the comet. So this is a picture of a nucleus of, I think, 67P. Not a short period comet expert, so I could be wrong. But basically, what we've learned from spacecraft missions is short period comets. So these are the comets that are most confined to the inner solar system. What we've learned that these comets are porous conglomerates of ice, gas, and dust. There's surface and subsurface outgassing. And the surface itself, from geomorphology taken from images of the comet from in situ spacecraft missions, we find that repeated sublimation creates complicated thermal processes, such as the creation of a dust mantle on the surface, thermal fracture, thermal fatigue. And this translates to, when we observe from ground-based telescopes, sublimation having a delay in onset of activity or occurring at a depth, and activity being quenched sooner than expected. So to address Jan Oort's hypothesis, we need to investigate the thermal processes that cause long period comets to fade. What is the explanation for non-typical sublimation on comets? And to do this, I systematically observed and analyzed nearly 100 long period comets activity by conducting a 3-year observational survey in conjunction with developing tools and improving models for sublimation, applying those models to the population and seeing what kind of trends we observe. And for the first time, this is possible because of the explosion and feasibility of all-sky surveys like ATLAS, Assassin, CanSTARS. Of course, those are the UH-affiliated all-sky surveys. There's other ones that exist, like Handling the Sky Survey and DTF. But essentially, we're talking about surveys that are so technologically advanced now. They're scanning the sky every night and being able to detect slow-moving objects, fainter objects. And so we're able to map out the activity of these targets over larger ranges of their orbits. And so now we can systematically look at their activity for a much larger population. And that's what my thesis aims to do. So this is going to be the structure of the rest of this talk. It was done. Right here is about the time you can take a bathroom break. Just kidding. Day reductions can be fun. Can be. So this is what I will be talking about, my 3-year survey. Briefly, some data reduction routines, model development, and then the fun stuff, getting into the science. So I know we have a lot of non-astronomers in the room and also on Zoom and YouTube. So I'd like to first talk about what it means to construct a light curve for a comet and the way that, broadly speaking, my observational survey is run. So it starts off with the discovery from an all-sky survey of a comet of interest. And I know about this because I'm subscribed to Minor Planet Center circulars, which basically tell me, hey, something has been discovered. It has an orbit it means it's probably an LPC. And I'm like, great, let's put it in our queue. So what the axis looks like here is this is magnitude, which is a measure of brightness. And for non-astronomers, astronomers, really like to make things interesting. So basically, larger numbers means fainter. More negative, lower numbers means brighter. So don't let that throw you off any of the plots, even though it throws me off all the time. So down here on the x-axis, this is a orbital parameter known as true anomaly. And basically it orients the x-axis with the perihelion, or the closest approach of the comet. 0 is where perihelion is. All negative values are pre-perihelion, so leading up to closest approach. Post-perihelion is positive values. So we have our first data point from discovery, and then what we do is use the Canada-France-Hawaii telescope on Mauna Kea within 1 month of discovery to take a follow-up observation. This is kind of a rough schematic of the orbit of a comet around the sun. You can see that this is point A and this is point B. As the comet gets closer to the sun, temperature increases, the dust tail gets larger, the brightness gets larger. And so you would expect the light curve, the brightness to go up. And so we're taking follow-up observations with CFHT, specific cadences within 1 month and several times over the next 6 months, in order to map out the light curve of each target. This is an example of how the target looks in some of the images. And then as it's going past perihelion, you notice the general behavior is that it gets fainter. And then when it's at its faintest, optimally, we like to use Gemini because it's an 8-meter telescope in comparison to CFHT, which is 4-meter, in order to get some of the faintest images of our targets that are either naturally faint or they're far out in their orbits. This little guy right here, that's the comet. So that's the general schematic of the observational survey. And our target selection is influenced by picking comets that are outside of the gravitational influence of outer planets. Essentially, we want both dynamically old and dynamically new comets, and comets with a range of activity and brightnesses. This means the most eccentric comets, E greater than 0.9 for astronomers, and comets that have the closest approach less than 10 AU, the furthest approach greater than 35 AU. So the technical information involved with this is that we use CFHT megacam, and we observe in the R-band filter. And this is because comets also have gas emission lines. So in other filters that are more blue, or like in the G filter, or in U, like the U filter, for example, emission lines are a lot more prominent. So this is a figure taken from Leach and Sabor in 2004. You can see there's a lot more emission lines at bluer wavelengths compared to our filter, which doesn't have a lot of gas emission lines. Because we're looking and hoping to model the behavior that's representative of the dust of the comet. So for CFHT images alone, we were able to take an average of 6 images per target, and that's for 83 targets. That's 3 years of telescope time, 5 semesters, 6 hours each, 10 targets per month. So a very coordinated follow-up survey. And then secondly, for Gemini, we were able to, for about 1/3 of our targets, get additional images for the targets that are faint out in their orbits, also using our estimates. So in conjunction with this, we also add archival all-sky survey data to construct our light curves. This is an example of ATLAS data that was retrieved from the COMA database from the COMA team, which is led by Karen Meach. And Daryl Manning specifically assisted me in retrieving this data, so thank you, Daryl. And ATLAS data works in both the cyan and the orange filter, and so that's what you're seeing here. These horrible streaks right here are just data points with extreme error bars. We get rid of those, so it's just an eyesore for now. And then secondly, we have assassin data, which is retrieved from the Assassin Sky Patrol Survey. Special thanks to Kyle Hart for helping with that. And so this is an example of what an assassin light curve looks like for one of the comets. Lastly, we retrieve minor planet-centered data for each of our targets. And so that's what all of this blue data is right here. Looks pretty messy. And the reason for that is just because minor planet-centered is a very nice hub where a lot of people report brightnesses of small bodies. And this doesn't keep track of information like filters or how they measure their brightnesses. So this often, and it's also from a large range of sources, so amateurs, astronomers, as well as professional sources. That's why we have a large scatter there. So we really only use the MPC data if we're looking to fill portions of the light curve that don't have data. Kind of the last resort. And then lastly, I use the JPL Horizons web tool, the fan line version, in order to retrieve all of what's called the ephemerides for the targets. Their heliocentric distance over time, geocentric distance, everything that assists with the modeling. With all of this data, it's very easy to get overwhelmed by the number of data points. And this only becomes a problem when we're starting to model. You can imagine that 1,000 data points is going to significantly increase computation time. And so for a lot of our data points, we bin our data, binning in true anomaly. And this allows us to also get rid of outliers from the general trend of the light curve. The really nice thing about this binning routine is that I developed it during my 699 project, which was about stellar evolution and chemistry. So it's just a really nice overlap of different areas of astronomy that can be compatible with each other. Okay, so what does adding all this data look like? Adding all this data together look like? So this is before any corrections, anything. This is just the raw data set, including both professional and all sky survey data. Looks terrible. That's okay, because we apply quality cuts such that we apply color corrections so that everything is in the R band. Everything with a noise greater than 1 magnitude is eliminated. We end up with something like this, zoomed in just so everybody in the back as well. Still kind of noisy. So we run it through our binning routine so that we're able to get rid of the outliers. And remember, we're not trying to make any physical claims about these outliers. It's possible that there are some short-term outbursts. That's not something that our model is able to handle. We're more concerned with general behavior long-term. So we run it through our binning model and we get something like this, much better. So this is raw data, or this is actual data of a comet. It's light curve, so how its brightness evolves over time. And then this is still too many data points. Believe it or not, this is on the order of 600 data points. So we bin this data and we're ready to feed it into the model. Now, a word on data reduction. All of the photometry that is gathered, all of the observations in our targets, both CFHT and Gemini observations, I utilize one of our Comet team members, Dr. Jan Kleine's automatic pipeline. So I'm very fortunate to have access to that, and that made the photometric calibration as well as the aperture photometry of these targets very reasonable. Thank you, Jan. So essentially we use a combination of source extractor and the PanSTARRS database to calibrate our images photometrically, and we do aperture photometry. Most of our targets use 5 arcsecond radius to measure the brightness. In addition to that, I also implemented the Gemini Dragons software to reduce Gemini images, and I had to add some additional reduction routines to get the images to be more photometric accurate. This is an example of a Gemini image with GMOS imager. You can see we have to get rid of some regions. Up here is where the telescope is vignetted. We have to get rid of that. And the outer chips are found to be non-photometric, so we have to get rid of those. We're often left with less than a third of the image. Okay, so now on to the fun stuff. So we have all our observations. How are we going to extract physical parameters from these observations for each target? So the main method that we use to assess volatile species and production rates, the surface ice sublimation model developed by my advisor. And I think for her own PhD thesis, maybe not. Yes? Wonderful. So this is actually kind of a legacy model. And this model itself, it computes the amount of gas sublimating from an icy surface exposed to solar heating. You can think of the way this model works is at a range of temperatures, ice will sublimate. This will occur at different heliocentric distances, depending on the volatile. As the cross-section of the coma will increase, this will cause a predictable change in the comet's light curve as it moves throughout its orbit. And we can calculate the magnitude contribution to the brightness as a function of the dust mass loss, dm over dt. And this mass loss is computed using the energy balance at the nucleus. And that energy balance equation right here. And so this is what the code does physically. And essentially, what you do in the way that it originally works is that you have a data set and you want to iterate through different parameters associated with the model so the model fits data. The parameters that are associated with the model are shown here. And so specifically and historically, the ones that have been iterated through most are nucleus size, grain size, fractional active area, which means what fraction of the area of the comet is active. And from that, we're able to derive volatile, fancy word for ice, and dust production rates. And so you can imagine that for singular comets, this code works very well. And in fact, it was validated by in-situ spacecraft missions to predict when a comet will turn on. And so when we look at this plot, again, light curve, there's nothing but light curves today. Not just light curves, but primarily. So we have our magnitude as a function of true anomaly. This is our data, and this is taken from Nietzsche et al. 2016. And this is the total model magnitude. This is the contribution from just the nucleus, contribution from water ice sublimation. And so this is a water and CO2 sublimation model. So this model was achieved by iterating through the parameters so that we can retrieve those parameters from the target. You can imagine that this can get exhausting for multiple targets. We're dealing with a sample of 100 targets. It's not quite feasible. So one of the so a large forming component of my thesis was to improve this model and augment it to have a more versatile usage. So I'd like to highlight just this one line right here, one line on one slide. Even though it doesn't have any associated plots, it is a large undertaking from generations of both graduate students and undergraduate students. I think in 2016, maybe earlier, undergraduate RU kind of sorely puts this model as a Python wrapped kind of function. So the model's originally written in Fortran, and you were able to call it with Python. And I'm very happy to say that after a large effort in continuing her work, I'm able to have written this fully in Python. So very proud to be a part of that legacy. And then secondly, I've added 4 parameters to quantize atypical activity in comets. So now let's look at this crazy looking plot, and I'll explain all of the forming components in just a moment. Inspired by answering Jan Oort's fading question, we want to be able to quantize different regions of cometary activity where this activity deviates from surface ice sublimation. And I colloquially call these fading parameters. And so TA1 shows when the activity turns on. TA2 is where you have the maximum fractional active area, or maximum activity. TA3 is where the activity begins to decline. And TA4 is where the activity is fully quenched, so just nucleus. This red line here shows the model without any fading applied. And in the background, it's a little hard to see, but this is the data associated with this specific target. And you can see that when we don't apply any fading, the model doesn't fit very well to it. In purple here, the model does fit well when we do have 4 additional parameters. So we're able to model different types of situations. If we have a delay in onset of activity, and then activity suddenly turns on, short-lived and then quenched, we're able to model that. Other situations where we just have a gradual onset of activity and a gradual fading, we're able to model that as well. And then, of course, the other 2 situations, you start off normal, and then the activity is quenched quickly. Or you have an outburst, and then the activity is breaking surface. So we're able to have multiple types of situations that we can now model. Lastly, the third major improvement that I made to the code was the augmentation of the code to improve Bayesian statistics. So a lot of you, I'm sure, are familiar with the MC model developed by Dan Foreman-Mackey. This is a Python function that is cited almost 10,000 times. And so it's very robust, very well used by the astronomy community. And the way that it works is that we have initial starting parameters for a model. So for example, we have a guess for the nucleus size. We have a guess for the fractional active area. And then we have 16 walkers that explore the parameter space around those guesses. And as they continue their walk, basically they're calculating the likelihood that the model fits the data. And if the likelihood goes down, they don't go in that direction. So essentially, you're mapping the parameter space of each of the parameters associated with the model. And from that, you're able to get probability distributions. And from that, averages and standard deviations for each of the parameters. So now we have statistics. That kind of random walk that I talked about for the walkers. So this is for a nucleus. This is for the fractional active area. All of these different little lines refer to different walkers exploring the parameter space. And as time goes on, they converge to a solution. This is the optimal case. So a static version of this. So these are the walkers. Eventually, after a certain time, they forget their initial starting position. That red line refers to the autocorrelation. To be conservative, we like to define the burn-in time as 3 times this. And what we do is we get rid of all of this information before the burn-in time, and we're left with this converged solution. And this is what it looks like. The average of this, the average of that parameter, and the standard deviation is the standard deviation of the parameter. We can also plot the probability distributions as a result of the walks. So this is what's called a corner plot. This is the probability distribution of the fractional active area for water. Oh my goodness, I have this labeled backwards. This is water FAA, and this is nucleus. My apologies. But basically, these are the probability distributions associated with each parameter, and this is the dependence of each parameter on one another with the 2 e's. So now going back to this plot, the reason why there are so many lines that we're showing here is something that's nice to see is taking random samples from that converged solution and plotting it over the data points to see the distribution of converged solutions. So this is kind of the variation of nucleus sizes that we would expect, and the variation of the total model magnitude that we would expect. And we're able to run thousands of models at once. We don't have to do this manually. We can make the computer work for us. So naturally, we want to be able to test the model to see if it works well. And to do this, we have used simulated comet data. So we have the original version of the model. We add Gaussian noise, backtrack. We have the original version of the model. We know its parameters. We have an output of the model. Then we add Gaussian noise. We remove regions of the light curve where we think the comet will be behind the sun. And then we have kind of a simulated data set that we feed back into the new model to see if it can recover the true parameters. And we vary things like noise, scatter, frequency of data points. And we run a series of tests to see how well we can recover these true parameters. The gist of the results of these tests are, not surprising, frequent data or a more populated light curve yields the best results, of course. So we need to have at least 100 data points, and then we need to have error that's less than 0.25 mag. This is just showing that as a function of number of data points, if we look at the percent from the true value, we notice that it only converges for high frequencies. And these are the associated Porter plots. You can see that we have forming Gaussian distributions only at high frequency of data points. This just looks like a mess. So, secondly, we are often dealing with targets that are active throughout all of their observations. Sometimes we don't observe them as bare nuclei. So this is an example of simulated comet data for a CO2 model. This is the contribution of the light curve due to the nucleus and this total magnitude. And you can see we never observe the comet when it's inactive, when it's a nucleus. In order to successfully retrieve the nucleus size, it needs to be at minimum, at max, 3 magnitudes from the light curve. Let's mix that up. And if it's not, then it cannot recover. For some of our targets, it can't recover. Okay, so now we have our observational survey. We have our tools to analyze our observations. Let's go ahead and model some comets. So this is some actual bin data, and the model applied to that bin data for C2019L3. That is a comet in my sample. And you can see this is a very nice example of when the comet is able to retrieve multiple parameters, including the nucleus size, as well as have a very nice fit to the data in terms of the total magnitude. You can see the contribution from water sublimation as well as CO2 sublimation. And yeah, so that's actual bin data that this is working for. I'm going to jump scare everyone with this corner plot. You don't have to read what's on here, that's okay. But this is just to show that for the model that I just showed, these are the associated recovered parameters, meaning that we're able to recover the nucleus size, CO2 and water fractional active areas, the fading parameters associated with both water and CO2. 11 different parameters with nice Gaussian fits, averages and standard deviations. It's not always the case though. Sometimes we get ugly looking corner plots, and that's okay, that's just how data works. So sometimes we have a comet where we can't constrain every parameter. And that's something that occurs in our sample. We have comets that have surface ice sublimation with no fading as well. And this makes about less than 15% of our population. This comet right here, C2021b2, meant to label it, but I've looked at these light curves for so long, I know exactly which ones they are. This is a water ice sublimation model. This is a CO2 sublimation model. Just surface ice sublimation. And so now, with our fading parameters, we can also see the extreme cases where comets have the abrupt onset of activity and abrupt quenching of activity. So now we're able to kind of infer the thermal evolution of the surface. So we have examples on the top panel of comets that suddenly turn on or suddenly produce an observable coma. The comets in the bottom of the panel where they suddenly turn off or are quenched. Their activity is quenched sooner than expected. And the reason why I have stars here is because in upcoming plots, these will be color coded. So yellow, abrupt onset, teal, abrupt quench. And I'll remind you. And then sometimes we have comets that have both. These are the most, in my opinion. So we have comets that have a rapid onset and rapid quenching, very short-lived activity. When we look at our population as a whole, and we want to see what kind of atypical activity dominates, we see that for the most part, in about 87 targets in our sample, comets primarily have CO2 fading, or I would say atypical activity associated with CO2 sublimation. So that's that top left plot there. These are bar plots where the gray is representative of the entire population, and this is split up into dynamically old and dynamically new. And we define dynamically old as aphelion or furthest approach, less than 1,000. Dynamically new is aphelion greater than 1,000. So, and apologies for the the small text. I've changed that, but that's okay. So this is a nucleus size as a function of aphelion, and these are comets that are unbound over here. So basically, their aphelion is so large that they're no longer bound to the solar system. If we look at this trend, it's suggested that it's a positive trend, but it's not statistically significant. So if we run something called a Pearson coefficient test to see if there is a positive correlation, we get a value of 0.3, which means that there's a weak positive correlation. And I'll discuss what this might mean in future slides. Now, if we look at the heliocentric, and yes, this was a little scary, I'll explain. If we look at the heliocentric distance associated with TA1, or the onset of activity, as a function of aphelion, which is loosely translated to dynamical age, we see that it appears there's a positive correlation. We run the same Pearson coefficient test. It's 0.39, which is on the cusp of the moderately. Plotting those with the extreme activity, the extreme onset and delay, show that they follow this positive correlation. And while not confirmed yet, it almost appears like there's two trends which may be representative of two different cometary populations. Now, the last thing we're going to look at is for those with both the rapid onset and the rapid quenching of CO2 activity. This population is enhanced in dynamically old comets. So, and this includes comets that only have sudden quenching, comets that only have sudden activity turn on, comets that only have turn on and quenching. So we notice that there's an overabundance of these in the dynamically old class. So putting all these three together, what does it mean? I theorize that this means that dust-mantle formation may be a contributing factor to these missing dynamically old long-period comets. You're like, wait a minute. I know you said dust-mantle formation at the beginning of the talk, and it's okay that you've forgotten exactly what that means, because I'll explain it here with my very high-tech drawing. So we can imagine that the surface of a comet, sublimation will occur for a dynamically new comet as it's going throughout its orbit. Sublimation lifts off dust grains of various sizes in the process, Dust grains that are too large will not be lifted off the surface and will accumulate, which will form something called a dust mantle. Dust mantle, dust crust, these terms are used interchangeably. And so large grains will eventually clog the porous medium of the comet, and a dust mantle is formed. The ice layer retreats deeper, and activity is quenched sooner than expected. It's an example of what might be happening for comets where their activity is like for this one right here. Then as the comet increases in dynamical age, as it goes through more dynamical iterations, this mantle layer will create a delay in onset of activity as it takes longer for the heat to penetrate the surface and cause sublimation. And that translates to a positive correlation with activity onset distance and dynamical age. As you go through successive orbits, it takes longer and longer for the heat to reach the retreating ice layer. Sublimation begins at a depth, adds pressure underneath the forming dust mantle, and eventually activity begins abruptly. And then the same process will repeat again, which again translates to that positive correlation that we see. The dust layer gets bigger, it takes longer for the heat to reach the lower layers, and eventually this potentially leads to thermal fraction. That weak positive correlation between nucleus size and dynamical age could mean that the nuclei are fracturing or getting smaller as you increase with dynamical age. None of this theory is new. All of this has been seen for short period comets. From spacecraft missions, from SPC studies, but this is the first time that this is seen on a larger scale for a large LPC population. And this is just a similar diagram from actual Institute spacecraft observation comet, looking at its geomorphology. So the theory is that based on our observations, dust mantle formation can be a contributing factor to why we don't see dynamic cold comets. With successive orbits, the dust mantle causes explosions of activity that are quickly quenched, which eventually leads to thermal destruction. And yeah, so that's it. That's the thesis. I've actually been here for so long. Wow, that sounds really fun. But I've seen a lot of my colleagues graduate, and I've seen a lot of acknowledgement slides. And I always think, how do you fit 7 years, 6 to 7 years of people in one slide? The answer is you can't. It's impossible. I'm so incredibly grateful for the assistance, the communities that I've built here in Hawaii that have helped me both as a scientist and as a person. This thesis in of itself is dedicated to my family, my mom, and my sister who's here today, and my niece, as well as my younger sister Emily, my dad, both from California, and my grandma. I'm very grateful for the science community that I have here, my committee, my advisor, all of the advisors that came before me. Koakai Canoe Club, of course, everybody in that, all of my Ohana Away from Home, Zach and Natalie Plater, Audrey Castaneda Walker, my partner Jackson Murphy, all of the secretaries here who've assisted in everything throughout the years, all of the graduate students here. Thank you so much.
And with that, I'll take any questions. Thank you.
Let's start with questions from the room. Yeah, Casey.
I have a question about the comets that have an eccentricity greater than 1.
Yes.
I thought that that was the definition of like these stellar objects. And so what's the difference between these unbound comets and one?
Great question. So we have comets that have elliptical orbits and then parabolic and then hyperbolic orbits. So those that have a significant eccentricity, that's much that makes it so that their orbit is hyperbolic, not parabolic. They're more likely to be ice. And then there are some comets that are just unbound, that are more likely to be dynamic. That makes sense.
I had a question about the, I guess it was the diagram showing the data over plotted with the models.
I'm sorry, which one? Sorry.
There's a lot of diagrams like this, but it showed the comet data with the different,
Yes.
the
I know.
improved model, just like one, for example.
Right.
Yeah, like one of these.
Oh, okay.
Or yeah, any one of them.
Oops. This one.
I was not sure. Yeah.
Typical.
So I noticed that some of them had, that you could see more of the walkers in them than others, and I was just wondering, like, does this just mean there's a greater uncertainty in the potential parameters which would fit this, or I don't know if you could go forward to.
So you're asking for the ones that have more parameters and a larger.
See the different like lines for each of the models. Some of them are really tightly clustered and make like almost a perfect fit, and some of them it seems like there's a lot more variation which parameters could be, or like some degeneracy in what could be giving that sort of like.
So I think the question is some parameters will have walkers that have larger distributions in their walking space, and is there like are those parameters less well constrained? Is that?
Yeah, or is there great, is it, yeah, is it,
They're more
is there,
uncertain.
yeah.
Yes, the answer is yes. Yeah, so you can imagine the random walk, if you have these walkers that have a large parameter space that has a huge scatter, that's going to translate to a larger standard deviation, and that's something that we.
Or data in the smaller part of the across the light curve.
Yeah, exactly. Yeah.
Okay.
I have a question about the dynamic comets. Have you seen any trends with different types of molecular species activity as a function of distance that can correspond to like ice lines?
Yeah. So I do look at the CO2 FAA and the water FAA as a function of acting. I don't see anything statistically. I don't see any statistical correlation. There's that warrants further study, I think, further interpretation. So,
Are there any questions in Zoom? I don't see any hands. All right.
So it seems to me, based on your observing campaign, you could potentially just get an absolutely enormous amount of comets from LSST for effectively free. Have people looked into that? Is that like one of the science cases where LSST will actually deliver?
I'm not too familiar myself with LSST, but I can imagine that in this day and age, as we get these surveys that like make the explosion of the detection of small bodies larger, we're going to have to come up with ways to handle that quantity of data. I do believe there is a projected estimate of an increase of detections of small bodies. I don't know what it is off the top.
Any questions in Zoom? I don't see hands, but you could just speak up. Any others in the room?
So here and related to the sources that fade very quickly, obviously it's getting faint, it's harder to observe. But if you don't have a constraint that tells you how close you actually are to just the bare, how do you know, like how is this particular pit so well constrained, well beyond where you have the observations? You're just relying on the slope and assuming that that activity continues, and that there's no slide of activity.
So we're making some assumptions here, and we're relying on the behavior of the light curve, the nucleus contribution to that behavior. So for a lot of these, we do have atlas data that is automatic photometry that I don't have images for. But if version 2 of this catalog, we do find that even at TA negative 100, those data points, the target does still have a tail, then we would say this is the upper limit size.
How did you handle bidding and kind of balancing like long, more average term activity with short like outbursts?
Yeah, so binning was done on a case by case basis. On average, the bins were 1 degree in true anomaly. So we want to have kind of a happy medium between still maintaining the frequency of the data points and getting the general behavior of the light curve while getting rid of kind of the short-term deviations. And so I would say like the outliers that are on the order of they're outliers because they deviate the curve 1 degree on the curve, something like that. Yeah. So, but it's done on a case by case basis because we don't want to be too conservative and get rid of too much of the light. I think there's somebody. Zach.
Oh, yes, Zach.
Hey, Erica, first of all, congrats on a great talk. My question is, so in my experience, a lot of times the things that take the longest amount of time and are the most in-depth work don't always make it into the talk. So I'm wondering what pieces of this, or I guess what piece was the most work, took you the longest, but doesn't actually make it into the talk?
A lot of these things took a long time, but I would have to say everything I talked about with regard to the sublimation model, specifically the MC augmentation, took the longest. That took several iterations of years to learn how to figure out basically. So, a lot of graduate students helped me with that, and I'm very, very grateful for that. So, yeah.
Amazing.
Any other questions? Well, if not, let's thank Erica.
We can have the notes to
Everyone.
that.